Great, thanks everybody. So I could be here talking about the psychology of the replicability crisis, and actually that wouldn't be too far off. My substantive area of research is self-deception and self-knowledge, so it's been a fascinating thing to watch from kind of the eye of the storm. So I'm a social and personality psychologist, which is, I think, one of the fields where this is really playing out a lot. And so I thought I would share some of my thoughts about what we've learned from our own kind of debates in psychology and what I think some takeaways are about how we should look at scientific claims more skeptically, I think. And that's one of the big takeaways for me of the replicability crisis in science. So when I was asked to speak here, one of the themes that we're supposed to talk about was, are we in a crisis? Are we doing things scientifically, et cetera? And I think in particular, as a psychologist, address this kind of elephant in the room: is psychology a science, with all the reproducibility and replicability issues that are coming up. And so I, over the last couple of years, have been trying to read some like baby philosophy of science and ask myself the question, well, what is a science? And I teach undergraduate research methods and graduate research methods, so I've been trying to think about like what is fundamental to the scientific process, and are we doing that in psychology? And so I've boiled it down to two phrases. What makes something a science is making predictions and testing them, and showing your work. And I'm going to talk about these two things and whether or not psychology is doing these things. And honestly, I don't think psychology is that different than many other sciences. I think we are failing to a large extent at achieving these kind of hallmarks of science, and I think other sciences are too. And we're trying to find ways to hold ourselves more accountable to these fundamental values of science. So it's no secret that psychology is in crisis. It's been all over the news. You can keep going and going and going. And then it spreads out to other sciences, so economics, science more broadly, social science more broadly. And as we've heard about today, it's including in the medical research, biology, et cetera. So recently, Manya Baker at Nature did a survey of scientists and asked, is there a reproducibility crisis? And the vast majority said there was, yes, either a slight crisis or a significant crisis. And these were mostly people in the physical and biological sciences. And they may be saying, yeah, over there in the social sciences, there's a crisis. I don't know. But I was surprised how high it is. In psychology, probably the most well-known sign or evidence of the crisis is the Reproducibility Project in Psychology, which was mentioned earlier. And this was a systematic pre-registered attempt with many, many labs involved, where they selected 100 studies that were published in the top journals in social, personality, and cognitive psychology. And 97% of those original studies had significant key findings. So that this is a graph of the p-values in the original studies. And this is consistent with broader literature reviews that find that over 90% of published findings in sciences in general and psychology in particular are significant findings. Null results basically don't get published. And so they took these 100 studies and tried to replicate them as directly as possible, but sometimes there were some changes that needed to be made. And then they ran the same null hypothesis significance testing test on the replication studies, and by that metric, only 37% reached statistical significance. Now, of course, there are probably some false negatives in there. The sample sizes for the replication studies were usually a little bit larger than the original studies, but still probably too small to really interpret many of those null findings. So we don't know exactly what the false positive rate is in psychology, but it's higher than we would like. Even if you double this, it's higher than we would like, right? The replicability rate is lower than we would like, even if it's twice 37%. So for those of you who might need a refresher, here's a slide from my undergraduate research methods class on type 1 error and type 2 error. So false positives are when we think there's something there, but there's not. And false negatives are when we miss something that's actually there. So there's a big debate in psychology about how we balance these types of errors, and should we be more worried about type 1 errors or type 2 errors? And I would argue that it's so easy to make something significant that really type 2 errors don't happen. Like if you have a research question, you want to find evidence for it, and you are willing to engage in these practices that are taught and are considered normal, or were until very recently, it's not that hard to find significant results and publish your findings. So not that many people walk away from a finding and say, oh, I guess it doesn't exist, I'm not going to try again, I'm not going to tweak the results. That's pretty rare, we think, based on surveys of research practices. So I'm not too worried about type 2 errors, but I am quite worried about type 1 errors. So the Reproducibility Project is one reason why, but other kind of studies, meta-scientific studies of research practices also provide a lot of reason for worrying about false positives. So I'm going to summarize a couple of things that we know happen. We know how they happen because we teach our students to do them. I taught my students to do these things, and I'm embarrassed about it now. But these were very common practices in psychology, and I suspect in other fields too, that produce false positives. So one is called harking, which stands for hypothesizing after the results are known. And this was the paper that coined this term was published in 1998, and we basically ignored it, and we kept teaching our students that you tell the story that sounds best after you know the result. You don't tell the story about what you intended to test, what you expected the study to show. You find the interesting result and you tell a story around that, and you say that you predicted it. So basically, you might have had a target when you started your study. You might not have hit that target, so just move the target and say that you found it, and then we all look like amazing archers, right? We're really, really good at hitting our targets, but many of those are capitalizing on chance, right? If we're willing to dig around and call anything that we find significant a predicted effect, then that's cheating. And it's also violating this fundamental norm of science that you should make predictions and test them, not the other way around, right? You don't make a prediction after you know the result. Prediction has the prefix pre. It's kind of amazing that we thought that this was okay to do. Another thing which was referred to earlier is what goes by p-hacking, or hacking the p-value. And I actually really like the phrase testing for a foregone conclusion. I think that's a really nice way to explain it in plainer English. It's where you want to find an effect. Your first test of it, your planned test, doesn't come out significant. And so there's ways that things you can do to see if you can get that p-value below 0.05. In the case of psychology, that's our alpha level, our threshold for statistical significance. So for example, you can check the data as they come in and stop collecting the data when the p-value dips below 0.05, as it necessarily will, even if there is no effect there. You can analyze many measures, but report only the ones that came out significant. And I should mention, I stole this slide from Leif Nelson's work, who is one of the 3 people that have really popularized this idea of p-hacking and false positives. Collect and analyze many conditions. You can use covariates. You can exclude participants. You can transform the data. So these are all signs. If these adjustments are made ad hoc in order to get a p-value less than 0.05, then again, you're capitalizing on chance. You're interpreting things that are probably just noise as if they were a real effect. And then the third is file drawing, which has been mentioned here also, which is if you still can't get a significant result after harking and p-hacking, then just stick it in the file drawer, don't report it, only report the studies that worked. So what these things do is they increase the rate of false positives, and they mean that they turn any old messy result into a beautiful, polished thing that you can tell a nice story around. So science ends up looking like this, when it should look more like that. I won't tell the other analogy. Maybe if you get me in private, I'll tell another analogy that one of my colleagues uses about what published science is, how distorted it is from what science really looks like before all that twisting and p-hacking. I'm going to skip this. So why not just do science right? There's a couple of reasons. One is embarrassing, is that we didn't know better. So it's not the case that scientists were doing these things knowing that they were producing false positives and then putting them out there anyway. Many, many of us, I would say the vast majority of us, didn't know the consequences of these practices on the false positive rate. And some of that is self-deception for sure. We should have known better. Some of it is we were so convinced that our theories were right, our predictions were right, or the result made so much sense after the fact, even if it wasn't the one that we predicted, that we thought, well, it's true, so why not put it out there? And the other one is that doing things right is really hard. And we are under all this pressure, right? We have to get grants, we have to get tenure, we have to get jobs. And the grants we get are tiny in psychology. So if people want us to do things the right way, then they should be giving us the resources to do that. And if we're given, fewer resources and smaller budgets and so on, and I'm still expected to produce X many publications a year, it's an impossible situation. So there's a kind of a perfect storm of incentives for us to take these shortcuts and believe the results that they produce. Still, when I give talks about this to people outside of science, they still just don't understand, right? This seems implausible that scientists would lead themselves down this road of so many false positives and fooling themselves. But I think Richard Feynman said it best, and he was talking about scientists when he said the first principle is that you must not fool yourself, and you're the easiest person to fool. And what's interesting to me is that as I mentioned, I teach first-year students' research methods. And what's really fascinating is they're, in the ways, the best scientists, right? They come in with all the right intuitions. They believe that you should make predictions ahead of time. They believe that you should try to prove yourself wrong, right? Falsifiability, we're trying to shoot down our theories, and that you should report everything you find. So this, in a way, they have it right, and we train that stuff out of scientists a lot of time, and the incentive structure, right, makes it impossible to live up to these ideal standards sometimes. So the incentive structure encourages cutting corners, and then overconfidence of researchers leads us to believe these incredible results, right? We can find things that seem amazing, and we want to believe those things. So there's again, a bunch of pressure from a lot of different places, and then the scientific community rewards scientists who can produce amazing results, and so that behavior is incentivized and rewarded, and it produces this vicious cycle. So for the second half of my talk, I want to get more concrete and talk about when we should be skeptical of a research finding. So this is going to be more specific to psychology, but I hope that there's lessons that can be translated to other fields, and they might look a little bit different in other fields. So what are some of the things that we now know from large-scale replication projects, from meta-science, that are signs that a finding is less likely to replicate or to be true? So one is small samples. So this has come up again earlier today. And what counts as a small sample depends on what you're studying. But in social and personality psychology, where we're studying multiply determined human behaviors like leadership or attraction, things like that, the effects are going to tend to be small. And so you need a large sample size often to detect them, a lot larger than we thought we needed. So one step for us is going to be to increase our sample sizes for most of our studies. I'm going to skip the empirical evidence that larger samples are better. It's pretty straightforward. Another sign that a finding is less likely to replicate is if the p-value is high and close to the threshold that is the threshold for significance in that field. So in psychology, it's 0.05. So if you see p-values very close to 0.05, 0.04, and that we can debate like how low does the p-value have to be before we count that as strong evidence. But given the current research practices, given p-hacking, et cetera, if you consistently see p-values just below that threshold or close to that threshold, that's a sign that there was some flexibility in the data analysis, that people were engaging in, probably unintentionally, probably unaware that they were doing it, engaging in p-hacking to get that p-value just below 0.05. There's a lot of simulations showing that when there is a true effect and you don't need to p-hack, the p-value is going to be very close to 0 most of the time. In fact, if you plot the p-values for true effects, they're right skewed. So most of the p-values are very close to 0, and then they drop off very quickly from there. So more than half, I think, are between 0 and 0.01 when there's a true effect. So if you're consistently seeing p-values of 0.03, 0.04 for a given set of studies, that should raise flags for you. Another one is if the research is not pre-registered, and that is almost 100% of research in many fields, right? So pre-registration has existed, for example, in clinical trials for a long time, but in many areas of research, it wasn't common to pre-register. So what is pre-registration? It's just making your prediction ahead of time and writing down what you're going to do. So again, this is from Leif Nelson's slides. They have Leif and his colleagues have a website, aspredicted.org, where you can fill out just 7 simple questions about what you're going to do, what you predict, and how you're going to test your prediction. And writing that down ahead of time before you collect the data will help prevent you from misremembering what you predicted, from going down this, what Andrew Gelman calls a garden of forking paths, where you give yourself many, many ways to find a significant result. This way you're kind of tying your hands. You're saying, this is my key analysis. If I don't find this, I was wrong. I can still explore, but then it'll be clear to everybody that all my other analyses are exploratory and should be interpreted as with less confidence, right? And another thing that should make us more skeptical of research findings is if the way they're reported is not open or transparent. So what do I mean by openness and transparency? I mean making the materials publicly available so that if someone wanted to replicate the study, they would have everything, they would know the procedure, the materials, et cetera. It means sharing data whenever that's possible, and there are cases when there are legal or ethical considerations that make it impossible, but in most cases in psychology, it should be possible to share the data, and that should make us trust the findings more if the authors do share the data. Disclosing flexibility in data analysis. So p-hacking isn't necessarily wrong. What's wrong about it is hiding it. So if people say, well, we first tried it without a covariate and that didn't work, so then we added a covariate and then it got a little closer, but it still wasn't quite there, so then we dropped some outliers and then it was significant. That's fine. I mean, we should have less confidence in that result, but that's okay for them to, as long as they're saying that they're doing that, right? But if they're only telling us this final analysis without the outliers and with the covariate and not telling us that how they got there, that's a problem. If a researcher wants to make a claim that they say is confirmatory, they predict it ahead of time, then they should pre-register that. Otherwise, we should say that it's exploratory. We should not hark. We should not pretend that we predicted it ahead of time. And I think it's important to value exploratory work. So in my definition of science as make predictions and test them and show your work, that kind of excludes exploratory work, right? If you want to make predictions and then test them, that means you have to pre-register and do confirmatory work. And I'm a big hypocrite because I've never pre-registered anything. But the way I see exploratory work is in generating predictions. So I think that it's really valuable to collect data, explore it, and find interesting patterns and present them as things that should be followed up on, that might be promising and might be worth a confirmatory study. And ideally, you would yourself do that confirmatory study before you publish. Some data are just so hard to collect, right? If you have a longitudinal data set, that kind of thing, it might not be reasonable to say, go and replicate that 30-year longitudinal study before you you publish it. So why is transparency so important? One is that I think it really is a hallmark of science. And this was put well by Lupia and Ellman, who said that open access to the origins of others' claims is the hallmark of scientific ways of knowing. It's what makes us different from claims to authority or intuition, that kind of thing. The motto of the Royal Society of Science is take no one's word, right? It's, I think, at the heart of it, what makes science different from other ways of knowing. As I was thinking about this, I also stumbled on another argument for transparency, which is much more pragmatic and less ethical. And I was reading a classic paper in economics, The Market for Lemons, Quality, Uncertainty, and the Market Mechanism. And in this paper, Akerlof argues that when there's an asymmetry in information between a buyer and a seller, as is the case in the used car market, so the seller knows a lot more information about a car than the buyer can't evaluate the quality of the product. And when the buyer can't evaluate the quality of the product, there's no incentive for the seller to sell high quality products, right? The consumers can't tell the difference, so they can pass off anything as a good product. But the buyer learns that the average quality is very low and then refuses to invest in the market at all, and trust goes down, and it leads to this spiral. And I realized that that's a good metaphor for what happens in science when there's not transparency. And so I wrote this up, that quality uncertainty erodes trust in science. So in this case, the sellers are the researchers themselves who know everything that went into getting that pretty significant result. And the buyers could be the journal editors or reviewers who are evaluating the work, or the broader community who's deciding whether or not to buy into that finding. And if we realize that the sellers, the researchers, are hiding a lot of critical information from us, and we can't tell a good product from a bad product, a solid finding from a bad finding, then we're going to start not trusting anything, right? So we need transparency in order for other people who read our work to be able to tell a solid result that we should have confidence in from maybe a suggestive one that needs to be followed up on, and then people will have more trust in the whole enterprise. But if we hide that information, no one's going to want to buy anything we're selling. And then if something hasn't been replicated, we should be more skeptical, although one of the lessons I think from psychology is that replications are only as good as the quality of the replication itself. So if every replication has all these signs of not being robust, so the replications are not pre-registered, they have small samples, et cetera, then that shouldn't necessarily increase our trust in the field. And we've seen entire literatures kind of collapse when a really robust pre-registered replication is attempted. And we see that even though there were 100 replications of a particular phenomenon, it can still fail to replicate under when it's really put to the test. And then a final thing that should make us skeptical, and this kind of sounds maybe anti-scientific to say this, but if something sounds too good to be true, that's another reason to be skeptical. And to the Bayesians in the room, that won't be a surprise. But this is also borne out by the evidence. So in the case of the Reproducibility Project in Psychology, where they attempted to replicate 100 findings, they also did a prediction market where people bet real money on which studies were likely to replicate versus not. So this is just testing people's intuitions just from what you can tell from a published paper. Do you think this is likely to replicate or not? And that market did quite well in predicting what would replicate and what wouldn't. So the black dots were successful replications, the red dots were failed replications by a certain metric, and the higher the dot, the higher the market price. So the ones that replicated did end up trading at a higher market price. So people's intuitions about what's likely to replicate are not useless. And if you see something that looks too good to be true, and especially if it has many of these other signs, of small samples, high p-values, et cetera, then I think it's reasonable to be skeptical of that finding and to want more evidence before believing it. I want to emphasize that even though psychology is getting a lot of the heat, I think that there are some good reasons for that, some reasons that I think psychology deserves praise. So I think we have been very self-critical in many ways, and we have done a lot to try to improve things. And I think that's to our credit, and hopefully will help other fields when they inevitably go through the same crisis if they haven't already. So some conclusions: science is really hard. I think we've been taking shortcuts, and we need to stop doing that. And the solutions are quite simple, I think. We need to make predictions and test them, and we need to show our work. So if we have more transparency, more accountability, we actually have to write things down in advance, make them public, et cetera. I think that will lead to a more scientific science. So in short, we need more transparency, more accountability, but also, and this has come up in many other talks, lower expectations. So this obsession with impact and this idea that every researcher should be making a huge discovery that's going to change the world is not healthy for science, and it's gotten us into a lot of these problems. And to address some of these problems, some of us started a group called the Society for the Improvement of Psychological Science, and we have annual meetings and a lot of different projects going on to try to change the incentive structures and make it easier for researchers to do more reproducible science. So that's it. Thank you.